Our universe holds secrets that rewrite the rules of reality. We will explore 30 deep space phenomena that baffle the world's greatest scientists, taking you to the very edge of human knowledge. From bursts of energy brighter than galaxies to a cosmic pull from the unseen, these are not just curiosities. They are glaring clues that our map of the cosmos is missing entire continents. By the end, you will see the night sky not as a static painting, but as a living puzzle of epic scale. What cosmic truth is hidden behind a star that winks like a machine? How can a vast sphere of space be almost completely empty? The answers are out there, waiting to redefine everything. Which mystery do you think will be solved first? The first clue arrived not from a telescope's careful gaze, but as a ghost in the machine. In 2007, astronomers sifting through old data from the Parkes radio telescope in Australia found something impossible. Buried in the recordings was a single, blistering burst of radio waves that had traveled across the cosmos for billions of years, yet lasted for just 5 milliseconds. In that fleeting instant, it released more energy than our Sun does in 80 years. This was the first recognized fast radio burst, a cosmic scream in the dark. Since then, we have detected hundreds more. These FRBs are not gentle signals. They are titanic explosions of pure radio energy, often originating from galaxies so far away their light is a fossil from a younger universe. Imagine the power of hundreds of millions of suns, focused and unleashed in the time it takes a camera flash to fire. That is the scale of these events. The strangeness deepens with their behavior. Most FRBs are loners, a single catastrophic flash from a point in space that then goes silent forever, but a defiant few are repeaters. They erupt again and again from the same patch of sky with no predictable pattern, like a temperamental cosmic lighthouse with a broken switch. This dichotomy has scientists chasing two different kinds of monsters. For the one-off bursts, the prime suspect is a cataclysm, like the spectacular collision and merger of two incredibly dense neutron stars, an event so violent it warps spacetime itself. For the repeaters, the focus has turned to magnetars, which are neutron stars with magnetic fields so intense they could erase a credit card from halfway across the solar system. The twisting of these magnetic fields might snap, unleashing these phenomenal bursts. Yet even these exotic explanations strain under scrutiny. Some bursts are too energetic, too frequent, or come from environments that do not fit. This has opened the door to far more speculative ideas, from evaporating black holes to vibrations in cosmic strings, theoretical flaws in the fabric of reality. The true nature of fast radio bursts remains one of astrophysics' most compelling puzzles, because each new detection is not just an answer, but a question written in fire across the universe. But the pull of the cosmos is not limited to fleeting bursts of light. Our entire galaxy, along with every star you can see, is caught in a relentless river of motion, heading toward a point in the darkness we cannot see. This is the mystery of the Great Attractor. Picture the Milky Way not as an island, but as a raft caught in a vast, slow-moving current. For decades, astronomers have known that our galaxy is not sitting still. It is moving at an astonishing speed of over 1 million miles per hour toward a specific region of space in the constellation Centaurus. This is not just our motion, but the motion of our entire local group of galaxies and thousands of others, all streaming in the same direction as if drawn by a cosmic magnet of unimaginable power. The source of this immense gravitational pull is what we call the Great Attractor, yet naming it is easier than seeing it. Its suspected location lies directly behind the crowded plane of our own Milky Way, in a region astronomers poetically call the zone of avoidance. This is not a place of emptiness, but one of overwhelming clutter. The disk of our galaxy is thick with interstellar dust, gas, and countless stars, creating a brilliant, obscuring wall that blocks our optical view of the universe beyond. It is like trying to see a distant mountain range through a blinding blizzard. For a long time, the Great Attractor was a ghost inferred only by the motion of everything around us. To solve this, scientists had to change their vision. They turned to telescopes that see in wavelengths of light our eyes cannot, like infrared and X-rays. These can pierce through the galactic dust, revealing the hidden architecture of space. What they found was not a single, monstrous object, but an immense concentration of mass, a sprawling supercluster of galaxies known as the Norma cluster, sitting at the heart of this gravitational anomaly. But here is the baffling part. Even this enormous collection of galaxies does not seem massive enough to account for the full strength of the pull we feel. This leads to an inescapable conclusion. The visible galaxies are likely just the tip of the iceberg, sitting within a far vaster, denser knot of dark matter, the invisible scaffolding of the cosmos. The Great Attractor, therefore, is not a destination but a waypoint. Our motion reveals that this entire region is itself being pulled towards something even larger and more distant, a colossal structure known as the Shapley supercluster. We are caught in a cosmic tug-of-war on a scale so vast it defies easy comprehension, reminding us that what we see in the night sky is only the smallest visible part of a hidden, dynamic, and deeply interconnected universe. This immense hidden mass pulling on our galaxy points to a far greater secret. The universe is filled with something we cannot see, touch, or directly detect. We call it dark matter, and it is the single most dominant architect of the cosmos we inhabit. Forget the planets and stars, the brilliant galaxies and glowing nebulae. All of that, every single atom you are made of and every speck of light you can see, accounts for less than 5% of everything that exists. Dark matter makes up roughly 27% of the universe, a silent, invisible presence that holds the entire cosmic structure together. The evidence for it is not a single observation, but a chorus of clues from across the universe. The first compelling note came from the way galaxies spin. Look at our own Milky Way. The stars in its outer arms orbit the galactic center at tremendous speeds. According to the laws of gravity, for those stars to whip around that fast without flying off into space, there must be a huge amount of mass in the galaxy providing the gravitational glue to hold them in orbit. But when astronomers add up all the visible mass from stars, gas, and dust, the numbers fall catastrophically short. There is simply not enough stuff to explain the motion they observe. The only logical conclusion is that a vast, invisible halo of mass envelops every galaxy, a halo of dark matter. This gravitational signature appears everywhere. We see it in the way entire clusters of galaxies move, their visible members dancing to a tune played by unseen hands. We see it through a phenomenon called gravitational lensing, where the gravity of a massive object, like a galaxy cluster, bends the light from more distant galaxies behind it, acting like a cosmic magnifying glass. The amount of bending we observe is often far too strong for the visible mass of the cluster alone. An immense, invisible mass must be there, warping the fabric of space itself. So what is this mysterious substance? We know more about what it is not. It is not antimatter, as that would annihilate with normal matter in a flash of detectable energy. It is not made of black holes formed from regular stars, as there simply are not enough of them to account for all the dark matter. The leading candidate for decades has been a theoretical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. The idea is elegant. These particles would be heavy, yet barely interact with normal matter except through gravity and perhaps the weak nuclear force, passing through our planet and our bodies as if they were not even there. This would explain why we cannot see or feel them, yet they exert such a powerful gravitational pull. For over 30 years, scientists have built exquisitely sensitive experiments deep underground, in mines and tunnels, shielded from cosmic rays, hoping to catch the faintest whisper of a WIMP colliding with an atom. The results have been a profound and growing silence. Not a single confirmed detection has been made. This persistent emptiness is forcing a radical rethink. Could dark matter be something even stranger, like a particle that interacts with itself in a hidden universe parallel to our own? Or could our very understanding of gravity be incomplete on cosmic scales? The truth is, after all this time, dark matter remains a placeholder name for a gravitational effect we cannot explain. It is the invisible skeleton of the cosmos, and we are still blindly feeling its shape in the dark. Yet the mystery of dark matter is only half the story. There is a second, even more dominant and perplexing force at work in the cosmos, one that is not pulling the universe together, but actively tearing it apart. This is dark energy, and it makes up roughly 68% of everything that exists. Its discovery in 1998 was a shock that overturned a fundamental assumption about the fate of the universe. For decades, the prevailing view was that the expansion of the universe, set in motion by the Big Bang, should be gradually slowing down over time. The collective gravity of all the matter, both visible and dark, was expected to act as a cosmic brake, pulling everything back together. To test this, two independent teams of astronomers set out to measure the expansion rate by observing a specific kind of stellar explosion in incredibly distant galaxies. These explosions, called Type 1 as supernova, are remarkably consistent. They always reach about the same peak brightness, which makes them perfect cosmic mileposts. By measuring how bright they appear from Earth, astronomers can calculate their precise distance. By also measuring how much their light has been stretched or redshifted by the expansion of space, they can determine how fast the galaxy was moving away from us when the star exploded billions of years ago. The results were not just surprising, they were revolutionary. The distant supernova were fainter than they should have been, meaning they were farther away than the slowing expansion model predicted. The inescapable conclusion was that the expansion of the universe is not slowing down at all. It is speeding up. Some unknown repulsive force, now called dark energy, is overcoming the pull of gravity and accelerating the expansion of space itself. This discovery earned the teams the Nobel Prize in Physics in 2011. So what could this force be? The leading candidate comes from an idea Albert Einstein himself once proposed and then famously discarded. In his equations for general relativity, he included a fudge factor called the cosmological constant, a kind of inherent energy woven into the fabric of empty space itself. This vacuum energy would have a repulsive gravitational effect, pushing space apart. Einstein initially added it to keep the universe static, a notion he later called his greatest blunder after Edwin Hubble discovered the universe was expanding. Yet, in a stunning twist, his blunder may have been a stroke of genius. The cosmological constant is the simplest mathematical fit for dark energy, but here lies the greatest embarrassment in all of theoretical physics. When physicists try to calculate how strong this vacuum energy should be based on quantum mechanics, their predictions are catastrophically wrong. The theoretical value is a number with 120 zeros larger than the tiny, gentle acceleration we actually observe. That is not just a small error, it is the single worst prediction in the history of science. This staggering discrepancy means our two most successful theories, general relativity for the very large and quantum mechanics for the very small, are fundamentally incompatible when it comes to describing the energy of nothingness. Dark energy is not just a mystery, it is a glaring signpost that our understanding of reality is profoundly incomplete, a silent, dominant force whose true nature remains the ultimate puzzle. This accelerating expansion driven by dark energy paints a lonely future for the cosmos, but it also deepens an older, more haunting question about our present. If the universe is so unimaginably vast and ancient, teeming with hundreds of billions of galaxies, each with billions of stars, then where is everybody? This is the heart of the Fermi Paradox, named for physicist Enrico Fermi, who, over a casual lunch in 1950, pointed out a staggering contradiction. The sheer scale and age of the universe suggests intelligent life should have arisen many times over and had ample opportunity to spread across the galaxy. The Milky Way alone is over 13 billion years old, and our solar system is a relative newcomer at 4.5 billion. That means there could be civilizations out there that are millions, even billions of years more advanced than our own. Given that head start, their presence should be obvious. They should have constructed cosmic-scale engineering projects, sent probes to every corner of the galaxy, or filled the heavens with signals. Yet we see nothing but silence. The sky is quiet. This profound absence is the paradox. To resolve it, scientists have proposed a spectrum of possibilities, some comforting, others deeply unsettling. One prominent idea is the concept of the Great Filter. This theory suggests that the evolution of life from simple chemistry to a spacefaring civilization requires passing through a series of incredibly difficult steps, like a cosmic obstacle course. One of these steps, the Great Filter, is so improbable that it stops nearly every civilization in its tracks. The terrifying question is, where is this filter located? Is it behind us? Were the steps from non-living matter to simple single-celled life, or from simple life to complex intelligence, so miraculously rare that we are essentially alone? Or more ominously, is the Great Filter ahead of us? Is there some catastrophic convergence of technology, resource depletion, or self-destruction that every advanced civilization inevitably encounters, a fate we ourselves may yet meet? Other solutions are less grim but equally mind-bending. The zoo hypothesis suggests that advanced civilizations are indeed out there and fully aware of us, but they have designated our region of space as a kind of cosmic wildlife preserve. They observe us without interference, following a strict principle of non-intervention until we reach a certain level of maturity or technological sophistication. Another possibility is that interstellar travel or communication is simply far more difficult and energy-intensive than we imagine, making galactic empires impractical. Perhaps sending physical probes across the gulfs between stars takes too long, or broadcasting powerful signals in all directions is a wasteful endeavor no advanced culture would undertake. There is also the sobering chance that we are simply too early. If intelligent life tends to arise only in the later chapters of a universe's story, we might be among the first civilizations to reach this stage, with others yet to emerge. The Fermi Paradox has no answer, only guesses, but its true power lies not in solving the silence, but in what the question forces us to confront about our own fragility, our ambition, and our singular, precious place in a seemingly empty cosmos. The profound silence of the cosmos does not mean we have stopped listening. Sometimes the universe offers a signal so bizarre it forces us to question everything we think we know about celestial mechanics. In the constellation Cygnus, over 1,000 light-years away, a star named KIC 8462852, better known as Tabby-star, began to behave in a way that defied all logic. Data from NASA Kepler Space Telescope, whose primary mission was to find planets by spotting the tiny, regular dips in starlight they cause, revealed something utterly different here. Tabby-star was not dimming by the predictable 0.01% of a planet transit. It was plunging into darkness by staggering amounts, up to 22%, as if something colossal and misshapen was drifting in front of it. These dips were not periodic. They were erratic, asymmetrical, and deeply variable, sometimes lasting for days, other times for weeks, with no discernible rhythm. Nothing in our astronomical catalog could easily explain blocking nearly a quarter of a sun's light. The most tantalizing and famously sensational hypothesis came from astronomer Jason Wright, who suggested the dimming pattern was consistent with a swarm of immense artificial structures, a Dyson swarm under construction by an advanced civilization to harness the star's energy. The idea of alien megastructures captured the public imagination, but scientists diligently pursued every natural explanation first. The leading candidate was a massive family of comets, perhaps thousands of them, on wildly eccentric orbits that could create a chaotic cloud of dust and ice. Others proposed the debris from a catastrophically shattered planet, creating a vast, uneven ring of fragments. More recent studies point to circumstellar dust, fine particulate matter orbiting the star itself, which could clump in strange ways. Yet each natural model struggles. A comet swarm of the required scale seems statistically improbable. Planetary debris should eventually clear or become more predictable. The dust appears to be the wrong size to explain all the light patterns. No single theory elegantly fits every bizarre observation. The true breakthrough in this mystery came not just from professional astronomers, but from a global army of curious minds. When funding for continued professional observation ran short, the lead researcher, Tabby, for whom the star is nicknamed, turned to the public through a Kickstarter campaign. Thousands of people donated, raising over $100,000 to secure time on a network of ground-based telescopes. This allowed for continuous monitoring, proving that citizen science could directly contribute to cutting-edge astronomical discovery. The data confirmed the dimming was real and complex, with the star also showing a long-term, gradual fading over years. Tabbys-star remains an enigma, a masterclass in scientific process. It is a reminder that when we encounter the truly unknown, our first instinct should be to explore every natural possibility, but also to have the courage to ask extraordinary questions. The most likely answer is a strange yet natural cosmic phenomenon we have not yet seen elsewhere, but the enduring mystery showcases the beautiful collaborative hunt for truth, where anyone can help stare into the depths and wonder what might be looking back. The search for cosmic intelligence is often met with profound silence, but once, just once, it seemed to speak. In the late summer of 1977, the Big Ear radio telescope at Ohio State University was performing a routine sky survey, listening to the hiss of the cosmos on a frequency near the hydrogen line, a logical channel for interstellar communication. On August 15th, the telescope's computer printed out a string of letters and numbers representing signal strength. The next day, astronomer Jerry Amon was reviewing the data when his eye caught a sequence so extraordinary he circled it in red pen and wrote a single, emphatic word in the margin: "Wow." The signal had lasted for 72 seconds, the exact duration the telescope's fixed dish could observe a point in the sky as the Earth rotated. It was a powerful, narrowband radio burst, focused on one specific frequency with no drift, meaning it did not come from a passing satellite or aircraft. Most compellingly, it matched the predicted signature of an interstellar signal perfectly. For that brief window, it seemed the universe had called. The immediate and enduring mystery is that the wow signal was never heard again, despite repeated and exhaustive searches targeting the same patch of sky in the constellation Sagittarius. Using increasingly sensitive equipment over decades, the signal never repeated. It was a cosmic one-hit wonder. This singular nature is what fuels both its legend and the scientific debate. Could it have been a human-made transmission reflected off space debris? The frequency was protected, meaning earthly transmitters were forbidden from using it, making that unlikely. A more recent natural explanation points to comets. In 2016, an astronomer proposed that two comets, which happened to be in that region of sky in 1977, could have been releasing large clouds of hydrogen gas which might emit at the right frequency. However, this theory has been widely challenged. The comets were not in the precise location of the WOW signal when it was detected, and the hydrogen emission from comets is typically much broader in frequency, not the sharp, narrow spike that was observed. So the mystery endures, a 72-second enigma etched on a faded printout. It stands as a haunting reminder of how difficult this search truly is. The wow signal is either a staggering cosmic coincidence, a natural phenomenon we still do not fully understand, or it was a fleeting, intentional beacon that swept past our planet and vanished into the eternal quiet. Its power lies not in an answer, but in the profound question it left hanging in the air, a question that continues to drive our listening. That profound silence from the stars is a product of our universe's ancient history, a history we can still see imprinted on the sky. The faint, uniform glow that fills all of space, known as the cosmic microwave background, is the oldest light in existence. It is the cooled remnant of the Big Bang's first fire, a baby picture of the universe when it was just 380,000 years old. This radiation is astonishingly smooth, a testament to the universe's early uniformity, but it is not perfectly even. Tiny, mottled variations in its temperature, mere millionths of a degree, reveal the seeds from which all galaxies would eventually grow. Yet within this subtle map of the infant cosmos, astronomers have found one feature that stands out not for its subtlety, but for its stark, chilling anomaly. In the constellation Eridanus, there exists a vast, circular patch of sky where the background radiation is significantly colder than anywhere else. This is the CMB cold spot, a region so large and so cold that it defies easy explanation. It spans nearly 1 billion light-years across, a staggering void in the thermal tapestry of the early universe. For such a pronounced cold spot to exist, something immense must have drawn energy away from that primordial light, leaving a cosmic shadow billions of years later. The most straightforward theory points to a supervoid. Imagine a region of space that is not just empty, but profoundly, overwhelmingly empty. A supervoid is a cosmic desert on a scale that dwarfs any other structure, a bubble in the universe's foam where galaxies and clusters are almost entirely absent. If such a void lay between us and the cold spot, the light from the cosmic microwave background passing through it would lose a tiny amount of energy as it climbed out of the void's gravitational well, an effect known as the integrated Sachs-Wolf effect. This would make the spot appear colder to our telescopes. The problem is one of scale. Astronomers have indeed found a large, underdense region in the direction of the cold spot, but the calculations are grim. This supervoid, as vast as it is, does not seem nearly sparse enough or large enough to account for the dramatic temperature drop we observe. It is like finding a small hill when the shadow calls for a mountain. This mismatch has led scientists to consider possibilities that sound like science fiction. One of the most mind-bending proposals is that the cold spot is a bruise, a scar from a collision with another universe in the multiverse. In this scenario, our expanding universe might have bumped against a neighboring bubble universe in the first instance after the Big Bang. The energy of that colossal collision could have drained away from that region of our cosmos, leaving it permanently colder. While this idea is theoretically possible within some models of cosmic inflation, it is extraordinarily difficult, if not impossible, to test or prove. The cold spot, therefore, remains one of cosmology's most persistent headaches. It is a feature too big to ignore, yet too strange to cleanly explain with the structures we see. It forces us to question whether we are misreading the shadows on the cave wall, or if the wall itself has a crack leading somewhere else entirely. Even as we map the grandest structures in the cosmos, the smallest discrepancies in our own backyard can whisper of hidden truths. This was the lesson of the Pioneer anomaly. For decades, as the twin Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the orbits of the outer planets and into the abyss, navigators noticed something deeply puzzling. The probes hurtling toward the stars were not moving quite as fast as they should have been. A minuscule, unrelenting force, equivalent to just 10 billionths of the gravity you feel on Earth, was acting as a constant brake, a gentle but persistent tug back toward the sun. This sunward acceleration was far too small to affect any mission objective, but for physicists, it was a glaring red flag. Every known force had been accounted for: the gravitational pull of every planet, the subtle pressure of sunlight itself, even the drag from the sparse dust of the interstellar medium. The math was checked and rechecked, yet the anomaly remained, a ghost in the machine suggesting our model of gravity itself might be incomplete at the solar system's edge. The mystery festered for over 20 years, a tantalizing hint of new physics just beyond our grasp. The breakthrough came not from a new telescope, but from forensic archaeology and thermal engineering. A dedicated team of researchers spent years recovering old data tapes and telemetry records, reconstructing the complete thermal history of the distant spacecraft. They realized a crucial detail had been underestimated. The plutonium-powered heat sources that kept the probes alive were constantly radiating warmth. This heat, bouncing off the spacecraft's main antenna dish and other surfaces, was not perfectly symmetrical. A tiny, anisotropic fraction of this thermal radiation was pushing back on the probes, like the gentle recoil from a warm light bulb. When this complex thermal recoil force was finally modeled with exquisite precision, it explained the vast majority of the anomalous drag. The case appeared closed, a triumph of meticulous detective work over exotic physics. Yet for some scientists, a whisper of the unknown remains. After all known effects, including the thermal push, are subtracted, a vanishingly small residual anomaly might still linger in the data, a discrepancy so tiny it borders on the edge of measurement error. Whether it is a final clue or mere statistical noise is still debated, but the legacy of the pioneer anomaly is undeniable. It taught us that to discover the universe's deepest secrets, we must sometimes listen to the faintest murmurs from our own creations, and that the path to revolutionary science often begins with a stubborn decimal point that refuses to behave. The faint whispers from our own probes are one thing, but in 2017, the cosmos sent us a postcard from a place we have never been. A telescope in Hawaii, scanning for near-Earth asteroids, spotted a faint point of light moving at impossible speed. Its trajectory was the giveaway. This object was not orbiting our sun. It was passing through, a visitor from the vast ocean between the stars. Named oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed interstellar object ever detected in our solar system. As astronomers scrambled to observe it, oumuamua revealed a cascade of oddities that defied every expectation. First was its shape. By measuring how its brightness changed dramatically as it tumbled, scientists deduced it was not round. It was profoundly elongated, shaped like a cigar or a pancake, with dimensions estimated at perhaps 10 times longer than it was wide. Nothing in our solar system looks quite like that. Then came the composition. As it sped closer to the sun, astronomers watched for the classic signs of a comet. When icy comets warm, they release gas and dust, forming a glowing halo called a coma and often a tail. Oumuamua showed no coma, no tail. It appeared utterly inert, like a dark, rocky asteroid. But then it performed its most baffling trick. As it swung around the sun and began its journey back out into interstellar space, its path could not be explained by gravity alone. Something was giving it an extra tiny push, a non-gravitational acceleration. Comets do this all the time as jets of evaporating gas act like natural thrusters. But oumuamua had shown no gas, no dust, no visible mechanism for such a push. The scientific community plunged into a fervent debate to explain this strange, speeding cipher. One natural explanation proposed it was a hydrogen iceberg. In the cold depths of interstellar space, a chunk of solid hydrogen could have formed. As it neared our sun, the hydrogen would sublimate, giving it a push without leaving a visible dust trail. The problem is, a hydrogen iceberg is incredibly fragile and would likely not survive the journey. Another idea suggested it was a chunk of frozen nitrogen, similar to the surface of Pluto. As the nitrogen evaporated, it could provide the thrust. Yet others argued it was simply a very dry, dusty fragment from a shattered planet, with fine dust too small to see providing the gentle propulsion. Then came the most provocative hypothesis championed by Harvard astronomer Avi Loeb. He argued we should consider the possibility, however slim, that Oumuamua was a piece of alien technology, perhaps a discarded light sail. A light sail is a proposed spacecraft that uses the gentle pressure of sunlight for propulsion, much like a boat's sail uses wind. Its flattened, thin shape could explain the unusual geometry. Its lack of a coma fit an artificial object, and the non-gravitational acceleration, that could be the pressure of sunlight itself pushing on a large, thin surface. The scientific pushback was immediate and fierce. Most astronomers firmly believe extraordinary claims require extraordinary evidence, and a natural explanation, however novel, is always more probable than an alien artifact. The debate was never really about proving it was aliens. It was about scientific methodology. Oumuamua challenged us because it left our solar system too quickly. We had only weeks of fuzzy observations before it vanished forever, a fleeting glimpse of something truly foreign. We will never get another look. It forced astronomers to confront the limits of their categories. Was it a comet, an asteroid, or something entirely new? Oumuamua, the silent scout, ultimately taught us that the galaxy is likely filled with strange, unseen travelers, and our next chance to understand them might already be on its way. Our galaxy is a predator. The serene spiral of the Milky Way, as we see it from Earth, is the result of a violent, ongoing feast. For billions of years, our galaxy has been consuming its smaller neighbors, a process astronomers call galactic cannibalism. Dwarf galaxies, containing perhaps only a few billion stars, wander too close to our galaxy's immense gravitational pull. They are stretched, torn apart, and finally digested, their stars scattered into the vast halo surrounding the Milky Way's disk. We can still see the evidence of these ancient meals today. Wrapping around our galaxy are faint, arcing rivers of stars known as stellar streams. These are the ghostly remains of dwarf galaxies, their stars still moving together in a coherent flow, like cosmic breadcrumbs marking a long-finished banquet. The most famous of these is the Sagittarius dwarf spheroidal galaxy, which is currently in the process of being ripped apart, its stars smeared across the sky in a great loop. By studying these streams, we are reading our own galaxy's violent history written in starlight. But this gravitational violence has another, more spectacular product. Deep in the heart of the Milky Way, where stars crowd together in a dense, brilliant swarm, our galaxy's supermassive black hole, Sagittarius A*, reigns. This monster, with a mass 4 million times that of our Sun, is not just a passive sinkhole. It is an engine of chaos. When a binary star system, two stars orbiting each other, ventures too close to this gravitational behemoth, a cosmic catastrophe unfolds. The black hole's immense gravity can rip the pair apart. One star is captured into a tight, doomed orbit, while the other is flung away at a staggering speed, often over 1 million miles per hour. These are hypervelocity stars, and they are some of the fastest objects in our galaxy, moving so swiftly they are on a one-way trip out into the intergalactic void. The existence of these stellar cannonballs was confirmed in 2005, and they serve a purpose far beyond their dramatic origin. As a hypervelocity star races outward from the galactic center, it must travel through the Milky Way's vast, invisible halo of dark matter. Its path is subtly influenced by the gravitational pull of all that unseen mass. By meticulously tracking the speed and trajectory of these runaway stars, astronomers can essentially use them as natural probes. They are test particles flung through the dark, their motions revealing the distribution and density of the dark matter halo that binds our galaxy together. Each hypervelocity star is therefore a dual messenger. It tells a story of a violent encounter at the edge of a black hole, and it carries with it a faint map of the invisible cosmos it is fleeing through, a single point of light tracing the shape of the dark. Beyond the last known planets, our solar system does not simply fade into emptiness. It holds a frontier of frozen worlds, a vast donut of debris called the Kuiper Belt, where Pluto reigns as the largest known member. But out past this belt, astronomers have found a handful of objects behaving as if they are not alone. Their orbits are not random. Instead, they cluster together in a way that defies the gentle gravitational nudges of the giant planets we know. These are the extreme trans-Neptunian objects, icy bodies so distant that they take thousands of years to complete a single orbit around the Sun. Their peculiar alignment points to a single, staggering conclusion: the gravitational hand of an unseen giant. This is the hypothesis of Planet 9. The math suggests it could be a super-Earth, a rocky world up to 10 times the mass of our own, lurking in the perpetual twilight of the outer solar system. Its orbit would be a long, stretched ellipse, taking perhaps 15,000 to 20,000 years to complete one slow journey around the Sun. At its closest approach, it might come within a few hundred times the Earth-Sun distance, still far beyond Neptune. At its farthest, it would vanish into the deep freeze, hundreds of times farther out. This is not a casual suggestion. The orbital clustering of these distant objects is so statistically unlikely to happen by chance that astronomers have been forced to take the Planet 9 idea very seriously. It is as if you dropped a handful of marbles on a vast, flat table, and they all rolled to rest against the same unseen leg. The search for this phantom world is now a major astronomical endeavor. Telescopes scan the predicted swath of sky where calculations suggest it might be, looking for a single, faint point of light moving slowly against the background stars. The challenge is immense. It would be incredibly dim, reflecting only the barest glint of sunlight from unimaginable distances. Finding it would be a triumph of celestial prediction, akin to the discovery of Neptune based on its gravitational influence on Uranus. But the implications go far beyond just adding a new planet to our charts. Planet 9 could be the key to unlocking several other solar system mysteries. One of the most puzzling is the Sun's slight but persistent tilt. The plane in which all the planets orbit is tilted by about 6 degrees relative to the Sun's equator. Why a massive, inclined orbit from Planet 9 could have slowly torqued the entire solar system over billions of years. Its gravitational influence might also explain the peculiar orbits of some objects that are perpendicular to the planetary plane, and even the mysterious Kuiper Belt Cliff, a region where the population of distant objects seems to abruptly drop off as if something swept the area clean. The existence of Planet 9 would force a complete rewrite of our solar system's formation story. How did a planet that massive form so far from the Sun? Was it born here and flung outward by a gravitational encounter with Jupiter or Saturn? Or is it a rogue planet captured from another star that passed near our infant Sun long ago? Each possibility paints a more dynamic and violent early solar system than we once imagined. Until we see it, Planet 9 remains a shadow in the equations, a gravitational ghost whose potential discovery reminds us that the most familiar places can still hold the greatest surprises. Our solar system's hidden giants could rewrite its history, but the history of our own planet holds a paradox just as profound. Billions of years ago, when the first oceans formed and life began to stir, our Sun was a weaker star. Nuclear fusion models are clear. The infant Sun shone with only about 70% of its current brightness. By all rights, that fainter, younger Sun should not have provided enough warmth to keep Earth's surface above freezing. The math is chilling. With solar output that low, our planet's early oceans should have been permanent sheets of ice, a global snowball state inhospitable to the chemistry of life. This is the faint young Sun paradox, yet the geological record shouts a different story entirely. In the oldest rocks on Earth, we find clear evidence of liquid water from that very era, ripple marks preserved in stone, minerals that can only form in wet conditions, and the fossilized signatures of microbial life itself. The Earth was not only unfrozen, it was warm enough for life to emerge and thrive. So what was keeping the planet cozy under that dimmer sun? Scientists have been piecing together a picture of a very different early Earth, one wrapped in a protective blanket. The leading solution points to a supercharged greenhouse effect. Our modern atmosphere is mostly nitrogen and oxygen, with carbon dioxide making up a tiny fraction. But back then, the air may have been thick with greenhouse gases, perhaps 30 times more carbon dioxide or a potent mix including methane, which is a far more effective heat trapper. This dense, primordial atmosphere could have acted like an insulating parka, trapping the sun's meager heat and preventing a global freeze. Another piece of the puzzle is the planet's reflectivity or albedo. Today, ice caps and clouds bounce a significant amount of sunlight back into space. The early Earth, however, may have been darker. With less continental landmass exposed, the surface would have been dominated by darker ocean water, absorbing more heat. There may also have been fewer reflective clouds, perhaps because there were fewer biological particles to seed them. Even the sun itself might have played a different role. While fainter invisible light, the young sun was likely far more temperamental, spinning faster and sporting a stronger magnetic field. This would have generated intense solar winds and more frequent, powerful flares. Some researchers suggest this barrage of energetic particles could have stripped away a primitive atmosphere, but others propose it might have triggered chemical reactions in a thicker atmosphere, leading to the formation of warming haze layers like the smog that shrouds Saturn's moon Titan. The true answer is probably a combination of all these factors, a delicate and dynamic balance between a faint star, a unique atmosphere, and a darker, water-rich world. Solving this paradox is more than an academic exercise. It tells us about the fragile recipe for a habitable planet and forces us to look outward. When we search for Earth-like worlds orbiting other stars, many of which are dimmer red dwarfs, we must remember that a planet's climate is not dictated by starlight alone. It is a complex conversation between a star and the world it embraces, a conversation that, on one world at least, whispered the first secrets of life into being. That ancient light from the universe's dawn holds another, even more unsettling secret. While the cosmic microwave background is famously smooth, its subtle patterns are not random. According to our most cherished cosmological principle, the universe should have no preferred direction, no special axis. The afterglow of the Big Bang should be a perfect, isotropic fingerprint, its hot and cold spots scattered like a celestial Jackson Pollock painting, with no alignment to anything in our local neighborhood. Yet, when scientists create a detailed map of this radiation, a bizarre pattern emerges. The fluctuations appear to whisper of a direction, an alignment that seems to correlate, against all reason, with the plane of our own solar system and even the direction of the Earth's motion through space. This unexpected correlation has been grimly nicknamed the axis of evil. The name is deliberately provocative, highlighting how deeply this anomaly disturbs cosmologists. If true, it suggests that our local cosmic address, our solar system's unremarkable orientation, is somehow imprinted on the oldest light in existence. This is not just unlikely, it is philosophically jarring. It would be like finding that the fossilized bones of the first dinosaurs were subtly arranged to spell out the latitude and longitude of your backyard. Such a connection violates the Copernican principle, the foundational idea that we do not occupy a special or privileged place in the universe. So what could explain this eerie alignment? The most hopeful and most likely answer is that it is a complex statistical fluke combined with subtle measurement biases. The data from space telescopes like WMAP and Planck is exquisitely precise, but untangling the true cosmic signal from foreground contamination is a monumental task. Our view is clouded by the diffuse glow of our own galaxy, the dusty plane of the Milky Way that cuts across the sky. Removing this foreground light to see the pristine cosmic microwave background beneath is like trying to hear a whisper in a crowded stadium. And any imperfection in that cleaning process could leave behind artifacts that mimic an alignment. Some researchers have proposed that the anomaly arises from the way we process the data on a sphere, or even from the unexpected influence of the solar system's own dust. Yet, after years of analysis and increasingly sophisticated data cleaning, the axis of evil stubbornly persists. Its statistical significance is low enough to be dismissed by many as a curious coincidence, but it is just high enough and just strange enough to refuse to go away entirely. This leaves open a door to far more radical interpretations. Could it be that the universe is not isotropic on the largest scales? What if it has a subtle structure, a preferred direction imprinted during the violent inflation of the Big Bang itself? Or in a twist that would truly upend everything, could this be evidence that our observable universe is just one bubble in a vast multiverse, and the alignment is a bruise from a long-ago collision with another bubble? The axis of evil, therefore, is less a solved mystery and more a persistent thorn in the side of cosmology. It represents the tension between beautiful, simple theory and messy, complicated data. It is a reminder that sometimes the most profound challenge to our understanding of the cosmos is not a dramatic explosion or a missing planet, but a faint, unsettling pattern in the static of creation, a pattern that seems to know we are here. The quiet battle over cosmic alignments is a philosophical one, but a more violent war rages at the edge of reality itself. This is the black hole information paradox, a fundamental conflict that pits our two most successful theories of physics against each other in a fight for the soul of reality. On one side stands quantum mechanics, the rulebook for the subatomic world. One of its most sacred principles is that information can never be truly destroyed. Information, in this sense, is not just data, but the complete set of properties that define every particle, its spin, its charge, its quantum state. If you burn a book, the ash and smoke still contain, in principle, all the information needed to reconstruct every word. Quantum theory insists the universe always remembers. On the other side stands Einstein's general relativity, which describes gravity as the curvature of space-time. Its prediction for a black hole is stark and simple. The event horizon is a point of no return, a one-way membrane. Anything that crosses it, whether a star, a spacecraft, or a book, is lost forever to the outside universe. All the intricate information about that object is crushed into the black hole's singularity, a point of infinite density where the laws of physics break down. For decades, physicists could live with this standoff, trusting that the information was still in there, just locked away. Then Stephen Hawking changed everything. He showed that black holes are not completely black. Due to bizarre quantum effects at the very edge of the event horizon, black holes slowly leak radiation, now called Hawking radiation. This radiation is thermal, like the glow from a hot stove, and it carries no information about what fell in. Over eons, a black hole will evaporate through this process, eventually popping out of existence. And here lies the paradox. If the black hole vanishes and all that remains is this featureless thermal radiation, then the information about everything it ever consumed is gone forever. This violates quantum mechanics' core tenet, creating a fundamental inconsistency in the laws of physics. To resolve this crisis, physicists have proposed solutions that sound like science fiction. One leading idea is the holographic principle. It suggests that all the information about what fell into the black hole is not lost inside, but is instead encoded on the two-dimensional surface of the event horizon, like a cosmic fingerprint smeared on a sphere. The three-dimensional interior of the black hole is, in a sense, a projection of that information, much like a hologram that looks three-dimensional is created from flat film. When the black hole evaporates, this information on the surface could, in theory, be imprinted onto the escaping Hawking radiation, preserving it. Another, more radical proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, gentle gateway relativity describes. Instead, it must be a searing wall of high-energy particles, a literal firewall that would instantly incinerate anything crossing it. This protects information by ensuring it never actually enters the black hole, but it utterly destroys the relativistic picture of someone falling in smoothly. Both solutions are deeply unsatisfying, forcing us to abandon a cherished principle from one theory or the other. The information paradox is not a minor puzzle. It is a glaring signal that our understanding of reality is incomplete at the most extreme intersection of the very large and the very small. Solving it may require a new theory of quantum gravity, a framework that can finally make peace between these two warring descriptions of our universe. The struggle to understand black holes reveals a crack in our cosmic rulebook, but another, quieter contradiction hides in the very first atoms the universe ever made. The Big Bang was not just a moment of expansion, it was a forge. In the first few minutes, as the newborn cosmos cooled from an inferno, protons and neutrons fused to form the universe's first atomic nuclei, a process called Big Bang nucleosynthesis. The models for this primordial alchemy are spectacularly successful. They predict the amounts of hydrogen and helium we see in the oldest stars with stunning accuracy, a cornerstone of modern cosmology. Yet for one element, the prediction fails spectacularly. The universe seems to have only about 1/3 of the lithium-7 it should. This is the cosmological lithium problem. The oldest stars in the halo of our galaxy, pristine fossils from the early cosmos, consistently show this lithium deficit. It is as if the universe's recipe book has a glaring typo in the instructions for making its third lightest element. This missing lithium is a profound clue because if our understanding of the first few minutes is wrong, the foundations of everything that followed could be shaky. Scientists have chased this discrepancy down three main paths. The first possibility is the most thrilling, new physics in the infant universe. Could unknown particles, like certain types of dark matter, have been present during those first minutes, altering the nuclear reaction rates just enough to suppress lithium production? Or were the conditions slightly different, with more neutrons or a faster cooling rate than our standard models assume? This path leads to exotic revisions of our cosmic origin story. The second path looks to the stars themselves as the culprits. Perhaps these ancient stars are not the pristine time capsules we think they are. Over their billions of years of life, internal processes could have gradually destroyed or transported lithium from their visible surfaces down into their hotter interiors, where it would fuse into other elements. If this mixing is more efficient than our stellar models predict, it could explain the low observed levels without changing the Big Bang. The third possibility is more prosaic but equally important. We might be measuring wrong. Determining the abundance of an element in a star is incredibly complex. It relies on analyzing the delicate absorption lines in the star's spectrum and modeling its atmosphere's temperature and density with perfect accuracy. A small, systematic error in how we model these ancient stellar atmospheres could lead to a large error in the calculated lithium abundance. The lithium problem, therefore, is a masterclass in scientific detective work. It forces us to question everything from the fundamental particles present at the dawn of time to the intricate physics of stellar interiors and the precision of our astronomical instruments. This tiny discrepancy for a single element reminds us that the universe's oldest fingerprints are still being decoded, and sometimes the smallest clue can point to the largest truth. But the cosmic mysteries are not confined to grand structures or missing elements. They rain down upon us from the void. Occasionally, Earth's atmosphere is struck by a single subatomic bullet carrying more punch than a professionally thrown fastball. These are ultra-high-energy cosmic rays, and they are the most energetic particles ever observed in nature. Typically just a single proton or atomic nucleus, they arrive at the top of our atmosphere, moving at a fraction of a percent below the speed of light. packing energies so immense they are millions of times greater than what our most powerful particle accelerators, like the Large Hadron Collider, can produce. Each one is a speck of matter with the kinetic energy of a Major League Baseball pitch, concentrated into a space smaller than an atom. When such a particle slams into the air, it triggers a spectacular cascade, a sprawling shower of billions of secondary particles that rain down over an area the size of a city, which we detect with vast arrays of sensors spread across deserts or mountain plateaus. The existence of these particles is not the mystery, however. The puzzle is how they got here. According to our best understanding of particle physics and the cosmos, these ultra-high energy cosmic rays should not be able to travel very far. The universe is not empty. It is filled with the faint glow of the cosmic microwave background, the afterglow of the Big Bang. For a proton traveling at near light speed across millions of light years, this background radiation is not a gentle glow, it is a thick fog. The proton should interact with these microwave photons, losing energy with every collision in a process known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. Over immense intergalactic distances, this process should drain these particles of their extraordinary energy long before they could ever reach us. This creates a profound contradiction. The fact that we detect them at all means they cannot have come from the distant depths of the universe. They must originate from somewhere within our local cosmic neighborhood, within a few 100 million light years at most, a relatively small volume in the grand scheme of things. Yet, when astronomers turn their telescopes to the patch of sky from which one of these particles arrived, they often find nothing obvious, no cataclysm powerful enough to serve as the cosmic cannon that fired it. The hunt for the sources has been a decades-long frustration. Leading candidates include the violent hearts of active galactic nuclei, where supermassive black holes spew jets of matter at relativistic speeds, or the aftermath of catastrophic gamma-ray bursts, the most energetic explosion since the Big Bang. Some theories even point to relatively nearby but exotic objects, like giant flares from magnetars within our own galaxy, or the decay of hypothetical super-heavy dark matter particles lurking in the Milky Way's halo. The challenge is that these particles are electrically charged, so their paths are bent and scrambled by the magnetic fields that permeate interstellar and intergalactic space. By the time they reach us, they are no longer pointing directly back to their source. It is like trying to trace a raindrop back to a single cloud in a hurricane. The mystery of ultra-high energy cosmic rays is therefore a double bind. They cannot come from far away, but we cannot easily find what is firing them from nearby. Each detection is a message from a powerful, hidden engine in our galactic backyard, a message written in a code of broken atoms and twisted paths that we are still struggling to decipher. While the cosmos hurls its most energetic particles at us, one of our solar system's most breathtaking geometric mysteries spins in serene silence. At Saturn's North Pole, a perfect hexagon 20,000 miles across etches itself into the clouds, a six-sided jet stream of unimaginable scale. You could fit nearly 4 Earths side by side within this single storm. Unlike the fleeting hurricanes of our own planet, this structure is a permanent fixture, a precise polygon of winds whipping at over 300 miles per hour, and it has likely been there for decades, possibly even centuries. The sheer perfection of its shape feels artificial, as if drawn by a cosmic compass, yet it is a purely natural phenomenon that defies easy explanation. Scientists have recreated hints of such shapes in the laboratory. When a circular pan of fluid is rotated at different speeds between its center and its edge, the flowing liquid can sometimes organize itself into polygons, squares, pentagons, and yes, hexagons. This suggests the pattern emerges from deep, fundamental physics of rotating systems, but scaling that lab experiment up to a planetary atmosphere is another matter entirely. Saturn is a gas giant with no solid surface, a world of layered, churning fluids tens of thousands of miles deep. maintaining a razor-sharp hexagonal boundary in such a chaotic, vast, and stormy environment for a human lifetime is without precedent in our solar system. For over a decade, NASA Cassini spacecraft had a front-row seat to this wonder. Its observations revealed the hexagon is not just a skin-deep cloud pattern. It is a towering structure with roots that plunge deep into the atmosphere. Cassini watched as the hexagon changed color with Saturn's long seasons, shifting from a bluish hue to a golden brown as sunlight returned to the North Pole after its long winter, suggesting complex chemical changes driven by solar warmth. The spacecraft even listened to it, detecting strange radio emissions linked to the hexagon's dynamics. Yet, despite this wealth of data, no single theory perfectly explains its origin and incredible stability. Some models suggest it is a standing wave pattern, a stable oscillation pinned in place by Saturn's rotation and the eastward jet stream at that latitude. Others propose it is the visible top of a giant, rotating cylinder of fluid that extends deep down, with the hexagonal shape emerging from complex interactions between different layers of the atmosphere moving at varying speeds. The hexagon stands as a majestic reminder that our own solar system, for all its familiarity, holds profound and beautiful puzzles. It is a lesson in humility, showing us that the laws of physics can paint with a geometric precision we are only beginning to comprehend on a canvas as vast as a world. Deep within the heart of our galaxy, a different kind of signal is waiting to be understood. The core of the Milky Way should be a place of predictable chaos, home to a supermassive black hole, dense star clusters, and the spinning corpses of dead stars known as pulsars. All these objects can produce gamma rays, the most energetic form of light. But when astronomers meticulously mapped this radiation using instruments like the Fermi Gamma Ray Space Telescope, they found something unexpected. Alongside the point sources they could identify, there was a persistent, diffuse glow of gamma rays that formed a smooth, symmetrical excess around the galactic center. This galactic center excess is not just background noise, it is a distinct and powerful signal with no obvious source. The distribution of this glow is the first clue to its strangeness. If it came from known objects like pulsars, we would expect to see a clumpy, irregular pattern across the sky, matching where these individual objects are concentrated. Instead, the excess is remarkably smooth and spherical, centered perfectly on the Milky Way's core. This smoothness points to something far more pervasive, something that fills the space around the galactic center in a uniform halo. For many physicists, this immediately brought one candidate to mind: dark matter. The leading theoretical candidates for dark matter particles, like WIMP, have a fascinating property. When two of these particles collide, they could annihilate each other, converting their mass directly into energy and producing a cascade of secondary particles, including gamma rays. If dark matter is densely concentrated at the galaxy's center, as most models predict, then this annihilation could produce exactly the kind of smooth, symmetrical glow we see. The energy signature of the excess even matches what some models predict for certain masses of dark matter particles. It is a tantalizing possibility, a direct signal from the invisible stuff that shapes the cosmos. Yet, extraordinary claims demand the elimination of all ordinary explanations. The primary alternative is that we are seeing not a single new particle, but a vast population of extremely old, rapidly spinning pulsars called millisecond pulsars. These objects are faint and could number in the thousands in the crowded galactic center. Individually, they would be too dim for Fermi to resolve as distinct points of light, but their combined emission could blend together into a smooth excess glow. Distinguishing between these two possibilities, a dark matter signal or a dense city of dead stars, is one of the most pressing challenges in astrophysics. New telescopes like the upcoming Cherenkov Telescope Array are being built with this exact puzzle in mind. they will have the resolution to potentially pick apart the smooth excess into individual point sources, either confirming the pulsar explanation or deepening the dark matter mystery. The galactic center excess is a perfect example of a frontier where known astrophysics and the hunt for new physics collide. It is a signal written in the universe's most violent handwriting, and its true author remains just out of sight. Yet the precise speed of this expansion is now the source of a growing crisis. Two of our most trusted methods for measuring the universe's expansion rate, known as the Hubble constant, are giving us two different, stubbornly incompatible answers. It is as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. The first method looks back to the universe's infancy, using the detailed snapshot of the cosmic microwave background from the Planck satellite. By analyzing the subtle patterns in that ancient light, cosmologists can calculate how fast the universe was expanding in its first moments, and then use our standard model of cosmology to predict what the expansion rate should be today. This early universe method gives us a very precise number. The second method works in our cosmic backyard, measuring the present-day expansion directly. Astronomers use a cosmic distance ladder. They start with Cepheid variable stars, whose predictable pulsations allow us to know their true brightness, making them perfect mile markers. By measuring how bright they appear in nearby galaxies, we can calculate precise distances. Then they look for Type 1, a supernova in those same galaxies. Because these stellar explosions always reach the same peak brightness, they act as blindingly bright standard candles visible across billions of light years. By comparing the distance of these supernovae to how much their light is redshifted by the expanding universe, we get a direct measure of the current expansion rate. This late universe method, honed over decades, also gives a very precise number. The problem is, these two numbers disagree. The universe today appears to be expanding about 10% faster than the pristine early universe data says it should be. This discrepancy is called the Hubble Tension, and it has grown from a curious wrinkle into a full-blown crisis as measurements have become more and more accurate. The error bars have shrunk, but the gap remains. This is not a small statistical fluke. It is a glaring crack in the foundation of modern cosmology. So what could be causing it? One thrilling possibility is that we are missing a piece of physics. Perhaps dark energy, the force accelerating the expansion, is not a constant as Einstein's cosmological constant suggests. Maybe it has changed strength over the lifetime of the cosmos, or there is an additional, unknown component to the universe that started influencing expansion only after the first stars formed. Another line of investigation questions our local measurements. Could there be subtle errors in our understanding of Cepheid variable stars, or is our own galactic neighborhood inside a local underdense bubble that is skewing our measurements? The most profound possibility is that our standard model of cosmology, lambda CDM, which has been spectacularly successful, is simply incomplete. It assumes a specific recipe of ordinary matter, dark matter, and dark energy. The Hubble tension suggests that recipe might need a new, exotic ingredient, or that one of the proportions is wrong. This is not just an academic debate, it is a direct challenge to our story of the universe. One of these two exquisitely precise measurements is pointing toward a truth we have not yet grasped, and the entire field is holding its breath, waiting for the next round of data to see which path forward is real. The precise recipe of our cosmos is written not only in starlight, but in a hidden fingerprint glowing in the dark. Across the galaxy and far beyond, astronomers point infrared telescopes at clouds of gas, dying stars, and distant galaxies, and they see the same mysterious signature. It appears not as a single line, but as a series of distinct bands in the infrared spectrum, a set of emission lines that consistently appear together. These are the unidentified infrared bands, and they are among the most common yet puzzling spectral features in the universe. For over 4 decades, they have been detected virtually everywhere we look, from the swirling nebulae where stars are born to the dusty hearts of other galaxies billions of light years away. Their very presence is a profound message. They tell us that complex, carbon-based organic molecules are not rare curiosities confined to planets. They are a universal phenomenon, abundant and thriving in the brutal vacuum of interstellar space, amidst deadly radiation and extreme temperatures. The bands act like a cosmic barcode, but one we have not yet fully deciphered. The pattern is clear and repeatable, indicating a specific family of molecules is responsible, but matching that barcode to a known chemical here on Earth has been an exercise in frustration. The leading candidate for a long time has been a class of compounds called polycyclic aromatic hydrocarbons, or PAH. Imagine the soot from a candle flame. Those tiny flakes are made of PAHs, molecules built from rings of carbon atoms fused together in flat, stable sheets. In space, these molecules could form in the cool outer atmospheres of dying stars and be blown into the cosmos, where they are then excited by starlight to glow at specific infrared wavelengths. The idea is elegant, and PAHs do produce emission features that are close to the observed bands, but close is not a perfect match. No single PAH molecule, or even a simple mixture of known ones, reproduces the exact pattern and strengths of the unidentified infrared bands seen across different environments. It is as if we have identified the language of the message as carbon chemistry, but we are still mispronouncing the words. This persistent mismatch suggests the true carriers are something more complex, perhaps a vast family of related carbon compounds that are larger, more intricate, or structured differently than anything we commonly create or study in our laboratories. They might be molecules that incorporate other atoms like nitrogen or oxygen, forming prebiotic compounds even more elaborate than simple soot. The sheer ubiquity of these bands is what makes them so compelling. They reveal a universe that is chemically rich and surprisingly organic, painting interstellar clouds with the raw materials for life long before planets ever form. These unidentified bands are a quiet, glowing testament to a cosmic chemistry set operating on a galactic scale, producing molecules we have yet to name, and reminding us that the universe's most common recipes might still be waiting in our lab notebooks. This theoretical wall has a name, the Greisen-Zatsepin-Kuzmin cutoff. It is not a physical barrier, but an energetic one, a fundamental speed limit for cosmic protons across the vastness of space. The math is clear. A proton with energy beyond about 5 times 10 to the 19th electron volts should be constantly battered by photons from the cosmic microwave background. Each collision saps its strength, slowing it down over distances of a few 100 million light-years until it falls safely below this energy ceiling. This makes the universe a kind of cosmic prison for the most energetic particles. They should never be able to reach us from the distant cosmos. Yet, the data from observatories like the Pierre Auger Observatory in Argentina tells a different story. A handful of recorded events, mere whispers in their vast detector arrays, carry energies that blatantly surpass this theoretical limit. These are the super GZK events, and their existence is a direct challenge to our understanding. If the GZK cutoff is correct, then these ultra-high energy bullets cannot have traveled far. They must be local, originating from within our own galactic neighborhood, a bubble of space roughly the size of the local group of galaxies. But here we encounter the second half of the mystery. When astronomers point their telescopes back along the rough path of these super-energetic particles, they find no obvious cosmic cannon. No nearby active galaxy with a jet pointed right at us, no recent catastrophic gamma ray burst in a neighboring galaxy, no known object with the sheer power to accelerate a single proton to such mind-bending speeds. It is as if a gunshot rang out in a silent forest, but when you look, there is no shooter to be seen. This forces scientists to confront several unsettling possibilities. The first is that our understanding of particle physics at these extreme, unreachable energies is simply incomplete. The interactions between a proton and the cosmic microwave background might play out differently than our models predict, perhaps allowing these particles to travel farther than we think. A second possibility is that these are not protons at all, but heavier atomic nuclei like iron. A nucleus has a different interaction cross-section and might, in theory, survive a longer journey. But even this has problems, as such a heavy nucleus would likely be torn apart by the same background radiation over immense distances. The third and most thrilling possibility is that these super GZK events are not coming from distant accelerators at all, but are produced right here in our own cosmic backyard by something we have not yet discovered. Could they be the decay products of exotic, super-heavy dark matter particles lurking in the halo of the Milky Way? When such a hypothetical particle decays, it could release a burst of energy that manifests as one of these ultra-high energy cosmic rays. Or perhaps they are generated by relatively nearby but phenomenally powerful objects we have misclassified, like hyperflares from magnetars within our own galaxy. Each detection is therefore a twofold enigma, a particle that should not exist at that energy, arriving from a direction that points to no known source. They are cosmic fugitives, breaking the established laws of intergalactic travel, and their very presence hints at either a flaw in our fundamental physics or a hidden population of engines, silent and dark, operating just beyond the edge of our perception. Even the mightiest anchors of the cosmos can be torn from their homes. At the heart of nearly every large galaxy, a supermassive black hole sits in gravitational dominion, a monster weighing millions or even billions of times our sun's mass. We imagine these colossal objects as permanent fixtures, unmovable anchors around which entire galaxies spin. Yet theory and a handful of tantalizing observations suggest a far more dramatic fate for some. They can become runaway behemoths ejected from their galactic cores to wander the eternal darkness between the stars. This phenomenon begins with a galactic collision, an event of slow, majestic violence. When two galaxies merge over billions of years, their central black holes are drawn together by gravity, eventually forming a binary system, a pair of titans locked in a final, intimate dance. As they spiral inward, they warp the fabric of spacetime itself, emitting ripples known as gravitational waves. In most scenarios, they eventually coalesce into a single, larger black hole. But under the right conditions, the merger can become a cosmic catapult. If the two black holes have unequal masses or are spinning at different angles and speeds, the final burst of gravitational waves can be shot out in one preferred direction. Just as a rifle recoils against a shooter's shoulder, the newborn black hole can receive a tremendous kick in the opposite direction, a recoil that can launch it clear out of its host galaxy at speeds reaching thousands of miles per second. Another, even more chaotic mechanism involves a third black hole, perhaps from a previous merger or a smaller galaxy being consumed. This third body can disrupt the delicate binary dance, gravitationally slingshotting one of the black holes into the abyss while the others merge or are flung elsewhere. The result is a ghostly remnant, a supermassive black hole stripped of its stellar court, traveling alone through the intergalactic void. Finding these runaway giants is one of astronomy's great challenges. A black hole without a galaxy is incredibly faint. It may retain a small, hot disk of accreting gas, glowing as a quasar, but one that is moving rapidly and located far from any obvious galactic center. Astronomers must search for these rare, displaced quasars, or look for the subtle gravitational fingerprint of a massive, invisible object tugging on the thin gas that drifts between galaxies. A few compelling candidates have emerged, like a quasar billions of light-years away that appears to be racing along at tremendous speed, far from the core of a distorted galaxy. Confirmation is difficult as alternative explanations must be ruled out. Could it be a projection effect where a background quasar simply appears near a foreground galaxy? Or is it the aftermath of a complex multi-galaxy collision that has simply disrupted the host galaxy's shape? Each candidate is a detective story written in misaligned light. The hunt for these cosmic fugitives is more than a curiosity. If confirmed, they provide direct, dramatic evidence for the chaotic mergers that build galaxies and their central black holes over cosmic time. They also represent a new class of celestial object, invisible nomads carrying the echo of an ancient, catastrophic impact, forever exiled from the stellar cities they once ruled. Even in death, a star can paint the sky with geometry. Far from the chaotic explosions of supernova, some suns end their lives with a quieter, more structured elegance. One of the most stunning examples floats over 2,000 light-years away in the constellation Monoceros. Through a telescope, it appears not as a cloud, but as a vivid, blood-red box with dark rungs like a celestial ladder, earning it the name the Red Rectangle Nebula. This is no artist's rendering, it is a real cosmic structure, a bipolar nebula glowing with the light of hydrogen excited by its dying central star. The star itself, known as HD 44179, is in a final, delicate dance. It has exhausted its nuclear fuel and is gently puffing away its outer layers into space. What should be a simple, expanding sphere of gas is instead sculpted into an almost perfect X shape, with two hollow, cone-like lobes extending in opposite directions. The sharp edges and startling symmetry give the illusion of a three-dimensional rectangle viewed from the side, a masterpiece of astrophysical origami. The prevailing explanation for this precise form involves a dense, dusty disk that encircles the star's equator like a giant belt. As the star sheds its atmosphere, this disk acts as a barrier, channeling the outflowing gas toward the star's poles and funneling it into two opposing jets. We see these cones from the side, their edges illuminated by starlight, creating the X-shaped silhouette. Similar pinched waist shape other bipolar nebulae, like the beautiful Butterfly Nebula. Yet the red rectangle remains in a class of its own. Its symmetry is extraordinarily sharp, and the ladder-like rungs across its interior are a unique puzzle. These dark bands are likely caused by periodic ejections from the star, occurring in rhythmic pulses every few hundred years. Each pulse creates a new shell of dust and gas, and as we look through the length of the cones, we see these concentric shells in cross-section, like the rings of a tree trunk made visible. But why are these ejections so regular, and what physical process creates such crisp, evenly spaced rings? The star at the heart of it all is a close binary system, two stars orbiting each other in a tight embrace. This duet may be the conductor of this cosmic symphony, with gravitational interactions between the pair regulating the timing and even the shape of the outflow. The red rectangle, therefore, is not a static painting. It is a snapshot of a slow-motion ballet, a testament to how the intricate gravitational interplay between two dying stars can impose breathtaking order on the chaos of stellar death. It reminds us that the universe's beauty often lies not in raw power, but in the emergence of precise patterns from fundamental forces, a geometry written in glowing gas against the dark. The motions of galaxy clusters might be telling a story we cannot see. While we know our local group is being pulled toward the Great Attractor, a far more radical claim emerged from studying the universe on its grandest scales. By analyzing the subtle shadows galaxy clusters cast on the cosmic microwave background, a technique called the kinematic Sunyaev-Zeldovich effect, one team of astronomers reported something staggering. They found evidence that hundreds of clusters spread across billions of light-years were all streaming in the same direction at incredible speeds, as if caught in a vast, coherent river. This apparent motion was dubbed the dark flow. The implication was profound and unsettling. If real, such a bulk flow on such a colossal scale could not be caused by any known structure within our observable universe. The gravitational pull required would be unimaginable, suggesting the source lay beyond the cosmic horizon, in a region of space-time we can never see. Perhaps it was the gravitational tug of a neighboring supercluster in the multiverse, or the lingering imprint of a pre-Big Bang structure. It was a hint that our universe might not be an isolated bubble, but one piece of a far vaster, unseen architecture. Yet, extraordinary claims invite extraordinary scrutiny. The dark flow has remained one of cosmology's most heated controversies. Other research teams, using different data sets and methodologies, have failed to reproduce the result. They argue the signal is not a real flow, but a subtle artifact of how we process the incredibly faint cosmic microwave background data, a systematic error masquerading as a discovery. It could be statistical noise or an incomplete accounting for foreground emissions from our own galaxy. The debate is technical, fierce, and ongoing. This places the dark flow at a fascinating precipice. It represents the very edge of cosmological science, where the signal bleeds into the noise, and the desire to find something revolutionary wrestles with the rigorous duty to doubt. Whether it is a monumental clue to a cosmos beyond our own or a phantom in the data, its legacy is to keep us questioning the finality of our horizon. What if the greatest forces are the ones we cannot even point to? The universe's missing matter is not just the dark and exotic kind. Even the ordinary atoms, the stuff of stars and planets and our own bodies, are playing a cosmic game of hide and seek. From our most precise calculations of the Big Bang, we know exactly how many protons and neutrons, collectively called baryons, should have been forged in that primordial fire. Yet when we add up all the normal matter we can actually see in stars, galaxies, and glowing gas clouds throughout the observable universe, we come up staggeringly short. Roughly 30 to 40% of all the atoms that should exist are simply missing. This is the baryon problem, a quieter but equally profound cousin to the mysteries of dark matter and dark energy. It tells us we are not just blind to the invisible majority of the cosmos. We are also missing a huge portion of the visible universe's building blocks. So where did half the atoms go? The leading suspect is not a distant dimension or a new particle, but a state of matter so diffuse and so hot it has slipped through our observational nets for decades. Theorists call it the warm-hot intergalactic medium, or the WIM. Picture the grand structure of the cosmos not as isolated islands of galaxies, but as a vast three-dimensional spider web. The galaxies and clusters are the dense knots where the threads intersect. The WIM is the web itself, the gossamer filaments of gas stretching between these knots over millions of light years. This intergalactic medium is not cold and dark. It has been heated over the eons by the colossal shock waves from galaxy collisions, supernova explosions, and the furious outflows from supermassive black holes. This heating has turned it into a thin, searing plasma, with temperatures ranging from hundreds of thousands to millions of degrees. At such extreme heat, the gas is ionized, meaning its electrons have been stripped from their atoms. This makes it nearly invisible to traditional telescopes that look for the glow of cool, neutral hydrogen. Finding it requires ingenious detective work, turning the universe itself into a backlit screen. Astronomers hunt for the WIM by using the brightest beacons in the cosmos, distant quasars. As the brilliant light from a quasar travels billions of light years to reach us, it passes through these faint, hot filaments. The highly ionized oxygen and other elements in the WIM absorb very specific wavelengths of that light, leaving extremely subtle fingerprints known as absorption lines in the quasar's spectrum. It is like looking at a distant, brilliant lighthouse through a faint, hot fog. The fog leaves a specific shadow on the light that tells you its composition. This painstaking work, combining data from ultraviolet and X-ray telescopes, has begun to pay off. Scientists have started to find these telltale absorption lines, confirming that at least some of the missing baryons are indeed hiding in this vast, hot web. The hunt is slow and difficult, requiring immense patience and the combined power of the world's greatest observatories. But each detection is a crucial piece of the puzzle, mapping the invisible scaffolding that channels and feeds the growth of galaxies. Solving the baryon problem would complete our census of the ordinary matter in the universe, finally accounting for every atom predicted from its fiery birth. It would show us that what we thought was empty space is in fact a structured and dynamic ocean, the true cosmic backbone upon which the glittering cities of stars are built. The story of tabbys-star is a masterclass in how science confronts the extraordinary. After the initial frenzy around potential alien megastructures, a global network of telescopes, including the dedicated Los Cumbres Observatory, kept a patient, unwavering watch. They were waiting for the star to dim again to capture its secret in the act. When the next major dimming events finally occurred, the data revealed a crucial fingerprint. The star did not fade evenly across all colors of light. It dimmed more sharply in blue light than in red. This simple fact was a revelation. A large, solid object like a planet or a rigid megastructure would block all wavelengths equally, creating a uniform shadow. Dust, however, is different. Tiny dust particles scatter and absorb shorter wavelength blue light more effectively than longer wavelength red light, exactly what the telescopes observed. The evidence overwhelmingly pointed away from alien engineering and toward a vast, uneven cloud of fine circumstellar dust orbiting the star. This was not the end of the mystery, but a profound refinement of it. The scientific process had worked exactly as it should, following the evidence from a sensational hypothesis toward a more nuanced natural explanation. Yet the peculiarities remain. What is the source of this immense dust cloud? Why is it so clumpy and variable? Could it be the aftermath of a catastrophic planetary collision, or the debris from a shattered swarm of comets trapped in a strange orbital dance? The exact nature of this dust and the forces that sculpt it continue to puzzle astronomers. Tabbys-star no longer whispers of aliens, but it still shouts about a cosmic phenomenon we have never seen before, a reminder that the universe's natural palette holds shades of strangeness we are only beginning to perceive. These cosmic ghosts are not empty spaces, but galaxies themselves. In the dense Coma cluster, a team of astronomers pointed a unique telescope array called Dragonfly toward what should have been a quiet patch of sky. What they found was not a brilliant spiral, but a colossal, faint smudge of light. They named it Dragonfly 44. This object was as wide as our Milky Way, spanning some 60,000 light-years, yet it contained only about 1% of the stars. Its light was so diffuse, so spread out, that it had been hiding in plain sight, camouflaged against the blackness of space. Dragonfly 44 is an ultra-diffuse galaxy, a cosmic phantom. The real shock came when they measured its mass. By observing how fast its few stars were moving, they could weigh the galaxy. The stars were orbiting far too quickly. To hold them in place, Dragonfly 44 had to possess the gravitational grip of a galaxy like the Milky Way, meaning it had a mass nearly 1 trillion times that of our Sun. The math was inescapable. With so few stars, over 99% of that mass had to be dark matter. This was not just a wispy cloud of stars, it was a dark matter colossus wearing a gossamer veil of light. The existence of these ghosts poses a profound challenge to our stories of how galaxies are born. In our standard model, a massive halo of dark matter pulls in gas, which cools, condenses, and eventually ignites into stars. The more dark matter, the more stars you generally get, but ultra-diffuse galaxies like Dragonfly 44 break that rule completely. They have the enormous dark matter halos of major galaxies, yet they fail to make almost any stars at all. It is as if a giant factory, built with all the machinery for mass production, only ever made a handful of toys. So what went wrong in these cosmic nurseries? One leading theory is that they are failed galaxies. Perhaps they formed in the crowded, violent environment of a galaxy cluster like Coma. As they fell into the cluster's heart, the intense heat and pressure of the intergalactic gas could have been stripped away, robbing them of the raw material needed to form new stars. Their star formation was strangled in its infancy, leaving them frozen as ancient relics. Another idea suggests they lost their gas in dramatic bursts of feedback. Early, fierce supernova explosions from their first generation of stars might have blown the remaining gas clear out of the galaxy's weak gravitational grasp, shutting down production forever. There is even a more unsettling possibility. Could the dark matter in these halos be different? Perhaps it is warmer or less clumpy than the dark matter in galaxies like our own, preventing gas from cooling and collapsing efficiently in the first place. Each ultra-diffuse galaxy we find is a fossilized question. They force us to reconsider the delicate balance between dark matter and ordinary matter, and to ask why, in some places, the universe built cathedrals of shadow and called them galaxies. The rhythmic flicker of a dying star can echo with the precision of a clock. As matter spirals into the final maw of a stellar mass black hole, it does not always vanish in silence. Instead, the intense X-ray glow from this superheated accretion disk can pulse with a strange, repeating cadence. Astronomers call these signals quasi-periodic oscillations, or QPOS, and they are among the most intriguing heartbeats in the cosmos. Detected by space-based X-ray telescopes, these oscillations are not perfectly metronomic like a pulsar's tick. They are quasi-periodic, meaning the rhythm is dominant and repeating, but with subtle variations in frequency and strength, like a drummer keeping time with a human touch. Some of these signals are incredibly fast, flickering hundreds of times per second. This speed is the key to their origin, for nothing material can move that quickly unless it is skating on the very edge of oblivion. The leading theory places the source of these rapid beats in the innermost stable orbit, the final circular path matter can take before plunging irrevocably through the event horizon. At this critical boundary where space-time is twisted into a vortex by the black hole's spin, the accretion disk may become unstable. Hot spots of denser, brighter plasma could form in the flow, orbiting at nearly the speed of light. Each time one of these hotspots swings into our line of sight, we would see a brief spike in X-rays creating the rapid pulse. The frequency of these pulses would then be tied directly to the black hole's gravitational grip and, crucially, to its spin. A faster spinning black hole drags space-time around with it, pulling the inner edge of the accretion disk closer in, where orbital speeds are even more extreme, leading to higher frequency oscillations. In this way, QPOS act as a natural strobe light, illuminating the dynamics of spacetime itself in a region where gravity is king. Yet, for all the elegance of this model, the precise physical mechanism that creates and sustains these rhythmic hotspots remains elusive. Is it a vibration of the entire inner disk, a ringing like a struck bell, or is it a shock wave reverberating through the infalling matter? Different types of QPOS appear at different frequencies, suggesting a complex orchestra of processes playing out in the final moments before matter is lost forever. Decoding these cosmic heartbeats is more than an academic exercise. It provides a direct observational tool to measure the properties of black holes that are otherwise invisible, particularly their spin. By listening to the rhythm of matter in its death spiral, we are essentially taking the pulse of a monster, learning about its rotation from the final cries of the material it consumes. Each flicker is a message from the last stable orbit, a signal carved by gravity's hand in the most violent nursery of physics we can observe. But the final mystery on our list is not a flash of light or a hidden mass, but an overwhelming, staggering absence. In the constellation of Boötes, the herdsman, there lies a sphere of darkness so vast it defies human comprehension. This is the Boötes void, a region of space roughly 330 million light-years wide. To put that in perspective, if our Milky Way galaxy were the size of a grain of sand, the Boötes void would be a hollow sphere over 2 miles across. It is not a perfect vacuum, but it is so profoundly empty that cosmologists often call it the Great Nothing. Where a typical chunk of the universe that size should contain thousands of brilliant galaxies, the Boötes void holds only a few dozen. It is a cosmic desert on a scale that makes our local supercluster feel like a crowded city block. Its existence is a direct challenge to our best models of how the universe organizes itself. In the grand cosmic web, we expect filaments, knots, and voids, but voids are usually much smaller, intricate bubbles in the foam. The Boötes void is a chasm. One leading theory to explain such a colossal emptiness is the merging of smaller voids. Imagine soap bubbles on the surface of water, slowly drifting together and coalescing into one giant bubble. Over billions of years, smaller cosmic voids could have gravitationally influenced each other, their underdense regions expanding and merging to carve out this unimaginable hollow. Another, more speculative idea is that it is the imprint of an ultramassive structure from the very early universe, a region where matter was somehow siphoned away before galaxies could ever form. Yet the void is not completely barren. Those few dozen galaxies that do exist within it are like isolated islands in an ocean of nothing, and this leads to a haunting, almost philosophical question. What would it be like for a civilization to evolve on a planet inside such a void? Their night sky would be a study in profound loneliness. Without the glow of nearby galactic neighbors, the blackness between the stars would be absolute. The concept of a Milky Way, a great river of stars arching across the heavens, would be unknown to them. Their entire observable universe might consist of their own galaxy and a handful of faint, distant smudges. The cosmic background radiation, the afterglow of creation, might be their only clue to a universe beyond their island of stars. They could develop a complete and accurate science of physics, yet their cosmological model would be one of profound isolation, a universe seemingly made almost entirely of empty space with a few scattered points of light. They might look out and conclude they are truly alone. The Boötes void, this great nothing, serves as the perfect bookend to our journey. We began with bursts of impossible energy and invisible forces shaping everything. We end with a staggering absence, a reminder that the architecture of reality is defined not only by what is there, but by what is not. It challenges our models, stretches our imagination, and forces us to confront the sheer, awe-inspiring scale of the canvas upon which all these other mysteries are painted. In the end, the universe is not just stranger than we imagine. It is stranger than we can imagine. And the greatest discovery may be that the map we are drawing still has continents of shadow waiting to be filled with light. These 30 cosmic riddles are not isolated puzzles scattered across the void. They are threads in a single, magnificent tapestry, each one pulling on the others in ways we are only beginning to see. The true power of these mysteries lies not in their strangeness alone, but in their profound interconnectedness, revealing a cosmos where solving one enigma might unlock the door to many. Consider dark matter, that invisible scaffolding. Its gravitational signature is not just an abstract idea, it is the force that sculpts the ghostly streams of stars torn from dwarf galaxies. It dictates the frenzied paths of hypervelocity stars flung from the galactic core, and it may very well be the source of the smooth, ominous glow at the heart of our own Milky Way, the galactic center excess. Find the particle, and you do not just solve one mystery, you illuminate a dozen dark corners of astrophysics at once. Similarly, the fierce debate over the universe's expansion rate, the Hubble tension, is not a minor accounting error. It is a direct stress test for our entire standard model of cosmology. That stubborn discrepancy between the early universe and the modern one is like a hairline fracture in the foundation of a grand building. It forces us to ask if dark energy is truly constant, or if some unknown ingredient was added to the cosmic recipe after the first stars formed. This single number, the Hubble constant, has the power to rewrite our story of cosmic evolution from the first instant to the distant future. Even the seemingly small problem of missing lithium in ancient stars connects to the grandest scales. That tiny deficit in a primordial element could be a clue that exotic particles of dark matter were already at work in the universe's first 3 minutes, subtly altering the nuclear furnace of the Big Bang itself. It suggests that the invisible and the visible realms have been intertwined since the very beginning. This is the beautiful, daunting reality of modern cosmology. We are no longer simply collecting curiosities. We are reverse engineering a machine of unimaginable complexity, where every gear, every lever is connected. An anomaly in the motion of a distant spacecraft might whisper about gravity's secrets, while a geometric storm on Saturn hints at the fundamental physics of fluids on a planetary scale. The eerie alignment in the universe's oldest light, the axis of evil, challenges the very principle that we occupy no special place, a philosophical tremor that resonates through every other observation we make. These are not 30 separate problems, they are 30 symptoms of a single, glorious condition, our incomplete understanding. Each baffling signal, each unexplained motion, each glaring absence is a point of light in a constellation we have not yet fully traced. They paint a portrait of a reality far richer, more dynamic, and more wonderfully strange than the simpler universe we once imagined. The journey does not end with a list, it begins with a map, and we are only now connecting the first dots. From the hexagon at Saturn's pole to the void in Boötes, this journey has spanned the architecture of reality itself. We have stood at the edge of black holes where information vanishes, traced the ghostly pull of unseen giants, and listened for signals in a silence that speaks volumes. Each of these 30 phenomena, from the faint young sun that warmed our infant planet to the dark energy now tearing the cosmos apart, is more than a curiosity. It is a boundary stone marking the very frontier of human understanding. These are not failures of science, but its fuel. Every baffling observation, every stubborn discrepancy, is a question the universe has asked of us, and the pursuit of each answer has illuminated corners of existence we never knew existed. This golden age of cosmology and astrophysics is not defined by having all the solutions, but by having the courage to confront the problems. The telescopes scanning the void, the detectors buried deep underground, the theorists wrestling with equations, they are all engaged in a single, magnificent project, drawing a map of a territory that is still mostly dark. The next great revelation, the one that finally explains dark matter or resolves the Hubble tension or reveals the truth behind Tabbys-star, could emerge from data gathered tomorrow. We are all witnesses to this unfolding story, this grand, collaborative effort to read the cosmos. So as you look up at the night sky, remember that the stillness is an illusion. It is a canvas alive with mystery, painted with invisible forces and whispering with signals we are only learning to hear. Which of these cosmic secrets captures your imagination the most? Let the conversation continue in the comments below, and if you want to join the next journey to the edge of understanding, be sure to subscribe. The universe still has so much left to tell us.